The last type of interference we need to cover in topic 9.3 is thin film interference. Now, this idea of a thin film is best explained with a couple of examples, and those examples are things like a soap bubble or a layer of oil on water. So we're really just talking about one substance that's very thin sitting on top of another substance. There's lots of different examples of that. There's thin films that you can place on glass to make them less reflective, so there's a whole heap of different types of thin films, but a soap bubble or a layer of oil are probably the two best examples. To give you a more visual cue, here's an image of some soap bubbles, and you can see on those soap bubbles that you get this separation of colours, so sort of a bit of a rainbow effect. You see the same sort of thing with oil on water as well. We're going to look at why it is that occurs in this video and develop a couple of equations to deal with the interference patterns that occur. So to do that, we're going to use an example of a soap bubble. So we're going to consider a diagram and all the quantities that are important to go along with that. And the diagram that we're going to look at here, so imagine we've got a layer of a soap bubble that looks something like that. So above the soap bubble we have air. We know that the index of refraction of air is 1. The speed of light is going to be close enough to the speed of light in a vacuum, and the wavelength of the light that we're dealing with will be lambda. Inside the soap bubble we have a soapy water mixture where the refractive index is going to be greater than 1. We don't need to specify exactly what it is, we just need to know that it's greater than 1. That means that the speed of light in the medium is going to be v, and the wavelength will denote it as lambda s, s for soapy water. Below the soap bubble we have air again, so back to n equals 1, and the speed of light and the wavelength being lambda. Now, in this scenario, we need to consider a ray of light that's travelling towards the soap bubble. That means that we need to identify that there is an incident angle that we're dealing with, and that incident angle here is actually really quite small. So there's an important point to note here that theta is very small, and by very small we mean that it's effectively or very close to being perpendicular. So the scale of this diagram is a little bit out of whack, but it's made to look larger there, so it's easier to make sense of what's happening in this scenario. We're also going to label this as being point A. We know that that ray of light then will travel across the soap bubble down to here. It's going to be refracted. We're also going to see a little bit of reflection occurring with the ray travelling back up that way. We're going to call that ray X. We also know at the other surface, we'll call that point B, we're going to see some transmission, so again refraction occurring there. Not really interested in that ray, but we'll mention it anyway. And then we also have a bit of reflection coming back up to that top surface, and that's going to be at point C. And then we get more refraction occurring, and we have ray Y travelling out through there. Note here that X and Y are both parallel. So important point to note there, two rays of light coming back into that medium, and note that they're the rays that your eye would see, so X and Y being the two rays that you would see as the light travels back from that soap bubble, whether it's been reflected from the top surface or reflected from the bottom and then refracted again. Now we need to consider a few different points here, so we'll start off with point A. So at A we have the reflection of ray X. And the important thing to consider here, this sort of ties back into subtopic 4.5, it's moving from a less dense to a more dense medium, and hopefully you can recall that means that we're going to see a phase change. So that's going to result in a pi radian phase change. So in other words, it's going to invert the wave. So it's now going to be pi radians out of phase compared to what it was going in. The second thing there is the refraction of that wave that travels across. So from A to B, and in that situation there is no phase change. So any transmitted wave will never undergo a phase change. If we then look at B, we're only interested really in the reflected ray here. We don't really care too much about that refracted ray, as I said. So the reflection that occurs here is going to be from a more dense to a less dense medium. And so that's the opposite to what happens at A. And so what we see there is that there's again no phase change. And that's a really important thing to identify, because it's what's going to happen at point C is the key aspect about what's happening in this scenario. So at C, we likewise have refraction occurring, and so this is going to now be the refraction of ray Y, and that's also going to be no phase change. So again, travelling from one medium into another, whenever we have a transmitted wave, there's no phase change occurring. So they're the basics of what's happening at each of those boundaries. We now need to consider what that actually means in a bit more detail. And before we do, we also need to denote here that we have a thickness of this soap bubble. We're going to call that thickness D. So if we look at that path from A to B and back to C, you can see that that's going to be twice the distance D. So the path A to B to C is going to be twice D, so is 2D. So, and again here, keep in mind that that ray is just about perpendicular, so while it might look in this diagram that it's going to be slightly longer than 2D, because that ray is effectively just travelling straight across and then coming straight back again, it's going to be close enough to being 2D, but because of the exaggerated angles, it looks like it might be a little bit more, so just recall there that that angle is very small. So if that distance, if that value of 2D is equal to some multiple of the wavelength in the soap bubble, so in other words, m lambda s, where m is an integer, so m is equal to 1, 2, 3, so on and so forth. We then have that the two rays X and Y will be out of phase. And that's largely because the reflection of X means that it's pi radians out of phase compared to what it was going in. There's no phase change as the ray travels through from A to B, reflects off B, and then refracts again at C. And so if the wave has travelled a total distance longer that's some multiple of the wavelength, then those rays X and Y will be out of phase, and out of phase by pi radians. And if we have two rays that are out of phase by pi radians, that's going to cause destructive interference. So by having that reflection at the top surface interacting with a ray that's travelled through by some multiple of the wavelength, we get destructive interference occurring, and we can identify there that that value 2D is equal to m lambda s. Now we're going to do a little bit of derivation here that's not important for you to be able to follow necessarily, but I think it's important to have a good understanding of why equations come about or where they've come from. We know that c is equal to f lambda, so c being the speed of light, lambda being the original wavelength, but we know also from that then that f can be written as c on lambda, and because frequency doesn't change during reflection or refraction, we can identify that that's also going to be the same as v, so the speed of the wave in the soapy bubble, over lambda s. From there we can look at the ratio of c on v, and that will be equal to lambda on lambda s, so just manipulating that equation. The reason why we're doing it that way is because C on V gives us the refractive index of the soapy water combination, and so that's going to be equal to the ratio of lambda on lambda s, and we can then say that lambda s is equal to lambda on n. If we then substitute that back into the equation, we find then that 2d would be equal to m multiplied by lambda on n. And if we take that one step further, we end up with the equation that's in the data booklet, including these words at the beginning, destructive interference. So 2dn is equal to m lambda. So there's the equation. So all that's happened there is that the refractive index has been multiplied up onto the other side. If we then look at what would happen to have constructive interference, I won't go through the whole derivation in that much detail again. We'll instead just identify that if 2d is m plus a half times the wavelength, so we're saying that it's half or 1.5 or 2.5 and so on and so forth, then we would find that constructive interference will occur. And that's because as the ray X and Y travel out, they will now both be in phase, and so constructive interference, as I said. And like I say, going through that same sort of process, you could then show that constructive interference for a thin film is going to occur when we have 2dn being equal to m plus a half times the wavelength lambda. So that's they're the two important equations looking at interference for thin films. The last thing then to state is that when you look at the value of d, if that increases, then the wavelength is also going to increase. That means that light rays are going to travel slightly longer distances through the thin film. So when they're travelling longer distances, that's going to mean that it's a longer wavelength that's going to result in either constructive or destructive interference. And so as a result, we get that separation of colours as we saw in the bubble image earlier in this video. Now I'll just highlight here the quantities that we're dealing with. D is the thin film thickness. And that's in meters. N is the refractive index of the thin film. And that's just a ratio, so there's no units. M is an integer value. So again, that's just the value 1, 2, 3, so on and so forth. And lambda is the wavelength of light. And given that it's a wavelength, that's going to be in meters also. So there's the quantities that are important for constructive and destructive interference for thin film interference.